B011810210 Electronic Merituk Theory, Dr. Azfairul Azhar. My name is Nadia Swada binti Muzaffar Ahmad, and this is my metric number. I'm from AKG section 1. Today we're going to discuss about Poisson and Laplace equation.
Hi Dr. Fairul. So my name is Dorita Sarawak with number metric B011810210 from BEKG section 1. Our topic for this assignment is Poisson and Laplace equation. Thank you.
Assalamualaikum to our lovely doctor, Dr. Fairul Azhar bin Abdul Syukur. My name is Nordiana Betty Jeffrey. My metric number is B011810238. Our topic for this assignment is Poisson and Laplace equation. Assalamualaikum. Before I proceed to the introduction of Poisson and Laplace equation, there is two persons which is important and related to this equation. The first one is Simon de Laplace, year 1749 until 1827. He is French astronomer and mathematician. He also discovered the Laplace transform and Laplace equation. The second one is Simon Denis Poisson, year 1781 until 1840. He also French mathematical physicist whose name is attached to a wide area of idea, Poisson integral, Poisson equation, and many more. Poisson and Laplace equation. Poisson and Laplace equation are easily derived from Gauss' law in bracket for linear isotropic material medium. For the equation, we can get this one and this one equation. So I name the first one is equation 1 and the second one is equation 2. Next, by substitute equation 2 into equation 1, we can get this equation. So I name this equation as equation 3. And then this is for an inhomogeneous medium. For homogeneous medium, equation 3 become this one and equal to 0. And then the upper one is volume charge density, and the below one is electrical permittivity. This is known as Poisson's equation. A special case of this equation occur when PV equal to 0. For example, for a charge-free region. So from this equation, it's become like this. This is Laplace equation in Cartesian, cylindrical, and spherical coordinate. So this one is Cartesian, and this one is cylindrical, and the last one is spherical coordinate. Uniqueness theorem. The theorem is proved by contradiction. We assume that there are two solutions, V1 and V2 of Laplace equation, both of which satisfy the prescribed boundary condition. Thus, this one equation, first equation, and then V1 equal to V2 when it's on the boundary. We consider their difference, this one. VD equal to V2 minus V1, which obey this equation. So VD equals to 0 when it's on the boundary, and this is I name as equation 2. For equation 1, just now I show you this one for the equation. From the divergence theorem, we can get this equation. Then we let A equal to this and use a vector identity. So this equation is when we substitute A. This one is A. So after we derive, we can get this. But this one is equal to 0 according to equation 2. So we can get this equation. From equation 1 and equation 2, it is evident that the right hand side is vanished from this equation. Hence, this equation is equal to 0. Since the integration is only positive, so we can get this two equation, which is VD equal to 0 or VD equal to V2 minus V1. This one when constant everywhere in V. Okay. This is uniqueness theorem. If a solution of Laplace equation can be found that satisfies the boundary condition, then the solution is unique. Three things that uniquely describe a problem. The first one is the appropriate differential equation, which is Laplace or Poisson equation. And the second one, the solution region. The third one is prescribed boundary condition. As we know, a problem does not have a unique solution and cannot be solved completely if any of the three items is missing. Thank you.
Hello everyone, today I would like to explain about the general procedure for solving Poisson or Laplace equation. Okay, so first, if rho v equals to 0, this is equation for Laplace equation. While rho v does not equals to 0, this is for Poisson equation. So we can solve both equations by direct integration when v is function of one variable. V is potential different, or we can solve using separation integration when V is function of more than one variable. Direct integration when one variable, separate integration when more than one variable. Okay, solution is not unique but expressed in terms of unknown integration constant to be determined. Second, apply boundary condition to determine a unique solution for V. By apply boundary condition, we can make solution for the unique. We can solve the unique solution. Okay, third, after we obtain the potential difference, we can find the electric field, electric flux density, and current density. Okay, if required, we can find the charge. This is charge where rho s ds. Okay, where rho s is equals to dn. dn is normal components of d. Normal component of d. Okay, also we can find C equals to Q over V or I equal to V over I, where I equals to J dot ds. That's all. Thank you.
Thank you, Diana and Dorita. Next, let's move on to the exercise. Since we know rho v is not equal to 0, we will use the Poisson equation, which is del squared v equals to negative rho v over epsilon. The boundary condition for this v is equals to the boundary condition v for dz is equal to v naught and for dz is equal to 0 shows that v depends only on z, which means there is no rho or v dependence. So we will double integrate dv over dz equals to negative rho naught over epsilons. And when we integrate again for the yield, we will get negative rho naught squared over 2 epsilon plus az plus b, where a and b are integration constant to be determined by applying the boundary condition when z equal to 0, v equals to v naught. When z equals to d, v equal to 0, we will get negative rho naught d squared over 2 epsilon plus ad plus v naught, or when we rearrange the a, we will get rho naught d over 2 epsilon minus v naught over d. The electric field is given by negative del V equals to rho naught Z over epsilon minus A for A cap Z. Next, the net force is when we integrate rho V E dV, we will get rho naught as V naught A cap Z. And when we rearrange this equation, we will get rho equals to V over S, which means we will get rho naught V naught equals to 550 Newton per meter squared. That's all from us. Thank you.